All right, so last time we did something with um, transformation and domain repetition, geometry, and stuff like that, and we end up with a pretty cool scene for a beginner, right? We just have a bunch of weird-looking shapes repeating infinitely in all x and z dimensions, and they kind of converge periodically. So that's pretty good. One thing I did not point out or it didn't explain well was the domain repetition part. Well, if you think about it, it's kind of just like um, by modding the point that we're testing in our rate marching step, we basically, if it goes out of a certain region, then we pull it out by modding it. We're kind of reflecting the point back into our fundamental domain. And we just keep ray tracing it there. So that we're treating all the space as the space around the center itself. The equation was given in here. I mean, you can just think about it. It should be pretty straightforward. Right? It shouldn't take too much thought. So there you go. In this video, probably already spoiled here. The topic of this video is going to be point lights. Right. In our previous shaders, we strictly use directional light as light source since it's very easy to implement. It's just a direction. It's just a dot product. Dot product. There's nothing hard about it. Right? Actually, a more interesting way to light your scene is, first of all, let me just edit this a little bit. Let me make the scene more friendly for a point light, point light sources. So 2.5, let's see. So that's pretty good. That should work. But right now, our scene is lit with the directional lighting, right? You can see all the light comes from one direction. So point lights, right? Point lights. The point light makes the assumption that the light source. So let's just talk about one point light for now. So here is the position where the light is. Right, it has a certain intensity, a certain energy it emits, and all the light you can think of it is that if I draw this out, you can see this light gets distributed radially, right? And in 3D, you can think of a sphere getting pushed out, getting larger and larger, right? So there's something. So let's say the amount of energy that gets to point P, right? And say the distance between point P and the light source is R, and the original light intensity is I, right? There's something called the inverse square law for a point light source. So R, which is the distance between the point and the light source, squared. Maybe there's some coefficients here and there just for intensity purposes, but this is generally true. Like this is true, right? So what this means is that as the point gets further and further away from the point light source, the energy or the intensity of a light that it gets from the light source decreases, not linearly, but at the rate of an inverse square of the distance. Why is that true? Well, it's kind of unintuitive if we think about it, since we already talked about photons. We think in terms of photons, as photon travels in a direction, it never gets weaker. Like as a photon travels in vacuum, let's say, there's no participating medium. There's no little molecules or atoms that hinders these points. Here hinders the photons traveling. There's no scattering happening. So just the photon traveling in a vacuum, their energy does not decrease. So why is this true, right? So let's think about it in a different perspective. The point light emits light in a radially outward way. Therefore, the total amount of light is the same when you enclose, like, you take a slice of the sphere in its sphere of influence. So let's say this circle, if we add them up, right, the points that's emitting around this circle here. So let's call it circle 1 or whatever. In 3D, it will actually be a sphere. So in sphere C1, when we look at the surface, right, there's a certain the total sum of light that's on the surface of the sphere that we're enclosing here should be equal to the amount of energy that was emitted from the light at time t, right, where the light eventually radially travels out and expanded to this sphere here. So let's call this term I here. And we enclose a bigger sphere, call it C2. And this has to be true for C2 as well. If we integrate over the sphere surface, all the photons that travel through the sphere, they must add up to I. So we kind of have an interesting situation here. Right, so the surface of C2 must equal to the surface of C1 in terms of intensity. So what does this mean, really? Well, they don't equal to each other, but like, okay, here's what I was trying to say. The intensity doesn't change, right? Intensity doesn't change. So I1 is the intensity on the inner sphere, and I2 is the intensity on outer sphere. What changes is how much energy per area on the sphere. That's the unit that's changing. Because you only have so much energy, but as you're expanding out to include a bigger sphere surface, the intensity gets weaker on a per surface level. So if you take this point, sample this point, and this point will get more light than this point, just because it's on a sphere where light is denser, because it has a smaller surface. So if we do the intensity per area times SC1, right, we could do something like this. So this is intensity per area for the first sphere, and this is the intensity for the second sphere. We have something like this, right? So intensity of the first area, or let's try to compute the second area right now. So it will be whatever the intensity of the first area is, the ratio that we can expect for the second intensity sample point is whatever the original intensity is in the inner sphere multiplied by this ratio. And what exactly is this ratio here? Remember the equation for a sphere surface. Actually, I don't quite remember, but all I can tell you now is this ratio increases at a 1/r² ratio, right? So if we go 1 meter away, okay, so if we go out by r amount of distance, say if we take the point sample P1 and we move P2 outwards by an r amount, the energy will, if we use this equation, then we will lose the energy at this rate. So the intensity at P2 will be the intensity at P1 multiplied by 1/r². If we compare it to the energy loss right from the center, if that makes sense. So the R term is the distance between the point that we're sampling and the center of the point light. All you have to think about is that the light itself, or the photons, they don't lose energy on its own based on the distance that it travels. But the distribution gets weaker and weaker because the sphere gets expanded at a nonlinear rate. So that's why we have this inverse square thing right here. So there we go. So that's basically the gist of it. Here we're kind of, let's just try to implement this sunlight. We don't have a sunlight anymore. I guess all we have now is indirect light, right? So I guess we kind of have to delete this. Direct light, say it's 0. So all we have now is the indirect light, which is just basically the ambient occlusion. All right, so how do we actually add point light here? So let's see. Eventually I want multiple point lights, as you can infer from the title. So I guess we'll do this step by step here. So light P which is the position of light. Let's make it at the center and raise it up by 1. Okay. The R term, which is the radius of the point between the light, we can just put light P minus. Do we compute P here? No, we never compute P. That's kind of stupid. It's just P times RD, and then we can replace the. We're going to refer to this point a lot. So why don't we actually where do we refer to it twice? Here, so why don't we just pull it out like this? So light P minus P minus P. If you do the dot product of the vector itself, the return value is the length squared. Right? So nothing special about that operation. And the intensity of the light, just I, will be 1 over, light R squared, something like that. And we already know the normal of this thing, and so this is the point. Here we're computing the light properties. This is the intensity or the ratio. Actually, we can infer this a little bit. Now we need the direction, just like because we still need direction to compute the Lambert. The Lambert law is still true for point light, just like it was for directional light. Since light comes at a certain direction, and based on the direction, you only absorb a portion of. That's not true. Based on direction, the light distributes on a variable area, and therefore the intensity varies based on the energy per area on the surface that gets lit. So still need the light, which is, I'm just going to call the light direction. Remember L vector, when people say this, usually they mean the inverse light direction. So it's going to be a normalized vector from the light P minus P. So this is the vector L is from P to light P and normalized. So this is a unit vector. We had an old L vector for a light, which let's delete it for now. So direct light is x 0, 0. Dot normal and L. This is the Lambert. This is the ratio of the intensity here. This is the projected array ratio for the light intensity. So multiply this by the light. Let's define a light intensity here. Let's just call it 1. This is how much the light gets, and divide it by the ratio, which is the square of the distance. So here we can see a pretty rudimentary point light that kind of obeys the inverse distance, so it looks quite realistic. Here, one more thing we could do with this is to try to increase the intensity here. And as we increase the intensity, you'll kind of see that the light finally reaches to the other part of the geometry, and instead just focus on the center. In fact, let's raise it up a bit. I believe so. So we kind of have a problem right now because the problem is if we want this light to reach out to more geometry, we have to increase the light energy, but then the points shaded at the center would be too intense. Therefore, these values would get clamped to 1, and they'll look bad. Here, it looks kind of flat. This is the problem, like I already inferred to it last time, right? This is a problem of dealing with only low dynamic range for our lighting. What we need is really high dynamic range that's unclamped lighting, right? This problem can actually be negated or solved with toe mapping by dealing with lighting in high dynamic range. Then, as we're outputting it to the screen, we'll kind of toe map it to crunch it in a natural way to a screen acceptable range for the numbers. So we put 100 here, still a bit too much, right? So what we have to do is let's just raise it up a little bit, right? Actually, it doesn't look right yet because we don't have the shadow term here. So we kind of have to change the shadow a bit. Actually, we don't have to. Actually, we do, because here the shadow code, it assumes a couple of things. It assumes that we should be able to trace back from the light direction indefinitely. So that's definitely not what we will want. We actually have a destination point from the point which we travel from. So what we're gonna do, I don't know if okay, I don't know if my GLSL implementation allows while loop. So if I can do this, okay, this actually compiles, so I can actually use while loop. That's nice. So let's do a point. So let's say this is directional shadow. So directional shadow here. And here I want to do a point shadow. This is a shadow for the point light. You know, we're gonna do basically the same thing, right? Except we're gonna add a destination point. Now, what we can compute. Okay. We can kind of infer what L is based on the input here, so we don't need to input L again. So it's light P minus P, which is just the direction from P to light P, which is L in our case. And T max here is actually, the distance. There's a function called distance in GLSL, actually we can just use here from light P to P. Okay, so this is our point light stuff. So here we can just call point shadow. Right, I have no idea if this works or not. It probably doesn't work. So light P. Okay. I mean, it looks like it's working. I don't know. So why don't we take the light position for a spin? I think it's I time, right? Okay. Because in my own little shader environment, I always use U time. Use them for uniform. I time. Let's see if the shadow actually works here. I think it does. Well, that doesn't really say much, does it? Why don't we increase the range a little bit? Okay, definitely the lighting actually is working because you can see there's part of the, there you go. You can see the shadow a little bit based on where the light is. Okay, so there you go. That's the shadow for a point light. And what's cool about it, again, this is unfortunate because we're getting kind of an artifact here because we can't really deal with this high intensity value before I tell you about how to do tone mapping, which I don't want to crush it into the same video as when I introduce the light points. So what I'm going to do is to create a struct. I'm just going to, now what I'm going to do is try to make multiple lights that walks around with different color. So actually if I do this is a red light, right? Now it's starting to look very cool. So yeah, the plan is to have multiple of these light walking around. So that's the plan. Again, you can see kind of the shadow shadow after artifact. Let me turn them off by disabling soft shadow. You kind of see now we only have hard edges shadows. It's much clearer that the point shadow is working correctly. I'll talk about how to fix the soft shadow edge artifact a bit in another video, probably the next one. We'll see where we go. So now let's try adding multiple point lights. So in order to do that, I don't want a whole bunch of the same code, so let me try to pull this out a little bit. So for point light, all the information we need here first is the position, right? then it's the intensity I. Kind of a terrible word, but I mean terrible name, but whatever. Works. It works. So let's just point light. So lights. Let's call these P lights. Let's say we have 5 of them. So P lights 0. Let's try to define it here. P light count. This is so we have something. This is just so we can refer to. I mean, this is so we don't use a magic number, so we can refer to this point P light count macro when we do iterations instead of just putting 5 everywhere. So whenever we want to change the number of lights, we can just change one place and it works for everything. Okay, so P light. I think the constructor for shader looks like this, I believe. So 1, 2, 3, 4. And what's the first parameter for the light pointer? So first parameter is position. The second parameter is the intensity. So why don't we stub them in for all of them, right? Okay, so we got a bunch of point lights now. And what we need to do is to first declare direct light to be empty. Then we start accumulating them by iterating over all of them, right? P light index, P light index, P light count, P light index. So inside this thing, we start doing this. Yikers, we need to format this properly. There we go. Well, we obviously don't need the normal, so we can pull the normal out to be here. The light direction. Okay, so the rest of these things we need pretty much. We need all of them. So P lights, P light index dot I, this light intensity, and the light point, which is going to be P lights, P light index, P. So it doesn't work because index is, wonder why. Wonder why it doesn't work. Right. I'm not adding to it, I'm declaring new direct light. So there we go. Want it to be different color, of course. So I'm gonna, because it's kind of tricky aspect for this thing. There's no actual formula for it, for how the light should move. I'm just adding random stuff. Hopefully it works the way, I mean, there's some random stuff where I want to make it out of what's the word for periodic functions? Adding a period shift to it, maybe. So another line in the center that's perhaps blue, something like that. Maybe this color. Another yellow light. This kind of looks like a cop car or something. Let's add one more pink light. So you can kind of see that it's getting interesting, right? All right. There's a better way to do this, of course, which involves introducing noise functions. I don't want to talk about noise functions for now. Probably in a totally different series because it's just so out of touch with the basic geometry rendering. And we can see a lot of the points are kind of, they're kind of merging around in the same area because we don't really have a difference in the periodic function that we feed them. So why don't we just do that right now? kind of add the multiply by different numbers, time this by 3, or whatever, or we can just modulate this one's height even. Make this one travel really far away. Maybe, okay, maybe that's too far. 6 minus 1, and we multiply it by t, so time here. This one travels really slow. This one almost doesn't move, but wait, why is that blue one looking like this? Alright, so that is point light. I admit they look a bit weird, but hey, it's point light. It's point light, alright. Probably want them to move around a bit more than just in this region. And this blue light is really tripping me out. It doesn't really move on around the other area too much. What's the color for that one? Probably this one, right? God, what am I doing? All right, so that's the intro to point light. I mean, it doesn't look that great because I can't really boost up the intensity of things. It's kind of unfortunate. You know what, let me just 5 up on all those colors. Let me just show you what it looks like when I do this. So, without telling you what these functions actually are, I'm going to use them because this works. So, okay, let's take a look at this. Okay, these are not working anymore. Because, okay, I guess I have to clamp this. So, clamp. Clamp the result of this. Right, we should have done it before. This suggests we ensure the t for our mixed function input is between 0 and 1. Alright, so there's point light. There's point light. Very colorful. Looks kind of ugly, but I guess you kind of have to deal with it, right? A little annoying that you actually can't see where they are. We could add like spheres to them, right? But typically point lights don't get any of that. So removing the tone mapping, the horrible tone mapping line, the color looks really clamped. But if you put it back, you can kind of handle it. It's not that terrible. Still pretty bad. All right. Let's just change it to 2, possibly. Still not good. Well, I mean, I guess one thing I could do. Wait, hold on. I don't want that to be the 3. It's actually a typo. So there you go. That's point light. It's a party down here. So many point lights moving around. Doesn't really create any harmony though. All right. So there you go. That's the other possible light source we could use, which is point lights, besides the directional lighting. Save this. And yeah, I'll talk about how to deal with the pain of having to deal with. Yeah, we don't really have to think about low dynamic range lighting anymore after the next video. I think I'll try to present a solution to that, and there you go. That means we'll have more freedom with defining our light intensity and don't have to be very careful in the way we define light intensity, so that there's no clamping colors involved like what just happened here. So that is it, I think. Let's add one more thing, actually. This is really fun, sorry. I want them to be all one, because that means the point are kind of going inside. Well, actually, let's see. So where's camera? 2.5. What if we do 1.5? It's okay. So 1 is like going through them, right? What you could do is try to do exactly that. Right, you can see the shadows. It's very interesting. So there you go. There is point light. I will see you next time.